So we just received major new updates on 3I Atlas, and according to Harvard astrophysicist Avi Loeb, something fundamental is not lining up with what we expect from a natural comet. When telescopes observe 3I Atlas, what they see is not the solid object itself, but an intense glowing cloud surrounding it. Nearly all of the light we detect comes from dust particles floating around the object, not from the nucleus underneath. When the Hubble Space Telescope imaged it back in July, astronomers tried to measure the size of the solid body at the center. They couldn't. The dust was so thick and so bright that the nucleus itself was completely drowned out. All they could determine was a very wide size range that tells us almost nothing. Loeb describes this as a veil. We are seeing the glow of an enormous dust cloud, but we cannot see what is actually producing that dust. That alone is highly unusual. In most comets from our own solar system, the dust forms a halo, but the solid nucleus remains at least partially visible. With 3I Atlas, the dust creates an optical barrier. The nucleus is effectively hidden. That raises an obvious and serious question. If we cannot see the nucleus, how do we know how large this object actually is? Stay with me until the very end if you don't want to miss what happens next. Additionally, you can subscribe, enable notifications, or hit like at any moment if this has already captured your interest. Go full screen for the greatest experience, and let's discuss the recent changes. Astronomers try to work backward from brightness, but here's the problem. The brightness we observe can come from two completely different physical situations. In one scenario, 3I Atlas could be a large solid object, maybe 20 kilometers across with relatively little dust. In that case, most of the light would be reflecting off its surface. In the second scenario, the object could be much smaller, perhaps only 1 or 2 kilometers wide, but surrounded by an extremely dense and active dust cloud. In that case, most of the light would be scattered by dust particles. Both scenarios produce the same brightness in our telescopes. From brightness alone, we cannot tell which one is true. The only way forward is to understand the dust itself. And this is where the physics becomes deeply strange. Typical comet dust particles are about half a micron in size. A micron is 1/millionth of a meter. So these grains are incredibly small, roughly 1/100th the width of a human hair. This size happens to be ideal for scattering visible sunlight, which is why comet tails glow so brightly. The interstellar medium between stars is also dominated by submicron dust. That is the normal scale for cosmic dust. But the dust around 3I Atlas is nothing like that. Using physical constraints, Avi Loeb calculated the particle sizes required to explain what we are seeing. The result is startling. The dust grains must be at least 10 microns in radius, and some could be as large as 100 microns. That makes them 10 to 100 times larger than typical comet dust. Size matters enormously because of how sunlight interacts with particles. Tiny submicron grains are easily pushed away by solar radiation pressure. They are swept backward almost immediately, forming the familiar trailing comet tail within about a day. But a 10-micron particle behaves very differently. Mass increases with the cube of the radius. So a grain 20 times larger in radius is roughly 8,000 times more massive. Solar radiation barely moves it. These heavy particles can actually travel toward the sun for hundreds of thousands of kilometers before radiation pressure finally slows them down and reverses their motion. That is exactly what we observe. 3I Atlas produces a jet pointing directly toward the sun, extending at least 400,000 kilometers, roughly the distance from Earth to the Moon. This sunward jet was visible in July, remained through September, persisted after perihelion in November, and is still present now. Even more astonishing, it remains tightly collimated. Its opening angle is only about 8 degrees, meaning it is more than 10 times longer than it is wide. Normal comet tails spread out and become fuzzy. This jet stays narrow, coherent, and sharply focused while pushing against a solar wind moving at over 800,000 miles per hour in the opposite direction. For that to happen, the particles must be large, dense, and massive. Loeb showed that the particle size is constrained to a very narrow range. The grains cannot be smaller than about 1 micron. If they were, solar radiation would stop them too quickly, requiring impossible launch speeds far beyond what gas drag can provide. But they also cannot be larger than about 100 microns. Particles that large cannot be lifted off the surface of a nucleus several kilometers wide by gas flow. That leaves a narrow sweet spot around 10 microns. This alone is extraordinary. Comets dominated by 10-micron dust are almost unheard of. One partial exception occurred in 2014 with comet Bernstein, which showed a weak sunward glow attributed to large, slow dust grains. But even that effect was far weaker than what we see here. Loeb suggests a possible natural explanation. 3I Atlas may have formed in or passed through a molecular cloud, where larger dust grains can grow by sticking together. Over billions of years in interstellar space, the object may have accumulated these grains on its surface. But the numbers involved are staggering. The sunward jet contains roughly 10 million kilograms of dust, or about 10 quintillion particles. To produce the observed brightness, the total reflective surface area of these grains is equivalent to a spherical mirror 10 kilometers in radius. These particles are replenished over about a month, meaning the object must eject roughly 3 kilograms of dust every second just to sustain the jet. And that's only the dust. The James Webb Space Telescope measured a gas loss rate of about 500 kilograms per second after perihelion. The dust-to-gas ratio is around 0.7%, almost exactly matching the interstellar medium rather than typical solar system comets. Then there is the chemistry. 3I Atlas is releasing 8 times more carbon dioxide than water. Normal comets are dominated by water ice. Only one comet ever observed in our solar system showed a similar inversion, and even then, scientists never fully explained it. The odds of 2 unrelated objects formed in entirely different star systems, independently developing nearly identical extreme chemistry, are very low. Carbon dioxide sublimates at lower temperatures than water and behaves differently during outgassing. This may help explain the unusually large dust grains. Or it may indicate formation in a fundamentally different planetary environment. But perhaps the most unsettling detail is the optical thickness of the dust veil itself. Loeb calculated the scattering probability, the likelihood that a photon of sunlight will collide with a dust grain before reaching the nucleus. That probability depends on particle density, particle cross-section, and path length. For 3I Atlas, the scattering probability is approximately 1 at the nucleus radius. That is a critical threshold. Below 1, the cloud is transparent. Above 1, it becomes opaque. 3I Atlas sits exactly on the boundary. Enough sunlight gets through to drive sublimation, but barely. If the cloud were any thicker, sunlight would be blocked, activity would shut down, and dust production would cease. Maintaining this balance, naturally, would be an extraordinary coincidence. If the object is natural, this constraint implies a nucleus at least 1 kilometer in radius. Smaller than that, and the dust would choke off the process. But if the object is not natural, the dust veil could serve a different purpose entirely, shielding whatever lies beneath from direct observation. The dust cloud extends roughly 3,000 kilometers around the nucleus, while the sunward jet reaches up to 1 million kilometers. Imaging the solid body at high resolution becomes impossible. The object is genuinely hidden. Over 6 months, the total dust released would form a layer about 1 millimeter thick on a 10-kilometer object. That might sound thin, but in interstellar travel, a millimeter-scale dust shield would be extremely useful. At velocities of 60 kilometers per second, even microscopic grains carry destructive energy. A dust cloud in front of a moving object would act as a sacrificial shield, vaporizing incoming particles before they can cause damage. The geometry of the dust around 3I Atlas matches this idea disturbingly well. The veil is extended sunward, tightly focused, and stable despite the object rotating every 16 hours. For a natural comet, this is extremely difficult to explain. For an engineered system, it is exactly what you would design. Loeb is careful. He repeatedly states that 3I Atlas is most likely natural, but he also emphasizes that the physics does not fully fit. There are now at least 15 documented anomalies. Each one alone might be dismissed. Together, they form a pattern that resists simple explanation. Right now, 3I Atlas scores 4 out of 10 on Loeb's artificiality scale, where 0 is an ordinary rock and 10 is confirmed technology. He has stated it will never drop below 2, regardless of future observations. An international observation campaign is underway through January 2026. The next major milestone comes on March 16, 2026, when 3I Atlas passes within Jupiter's Hill radius, the gravitational boundary where satellites can be captured with minimal energy. Astronomers will be watching closely for unexpected trajectory changes, separations, or new objects appearing in Jovian orbit afterward. Whether 3I Atlas is an extreme natural comet or something else entirely, one fact is clear. It is hiding behind a veil of dust unlike anything we have seen before. We cannot see its nucleus. We cannot measure its true size. And with each new observation, the mystery deepens rather than resolves. For now, the object remains concealed, and scientists genuinely do not know what lies beneath. Let me know your thoughts in the comments.